Welcome back, everyone. In the previous lecture, we covered the motivation behind exploring both interaction terms and higher order terms. Now we're actually going to focus on how to create these polynomial terms with scikit-learn and Python. Let's head over to the Jupyter Notebook. All right, here I am in the Jupyter Notebook. I've gone ahead and imported NumPy, Pandas, Matplotlib.pyplot, and Seaborn, just in case we need to use those. And then I also read in our original advertising.csv file. And recall that we have three features: TV advertising spend, radio advertising spend, and newspaper advertising spend. Then we have the appropriate Y target label column, which is sales. So in order to actually create these polynomial features, it's more akin to feature engineering than creating a new model. Because what we're actually going to do is first separate out our features from our label and then use pre-processing to create changes or new features from our original three features. To do this, the first step is to actually separate out your X features and your Y label. So the easiest way, in our particular case here, to just grab all the X features is to grab everything but the sales column. So we'll say df drop sales x is equal to 1. Those are all our X features. And then we'll say Y is simply equal to df sales. And now it's time for polynomial regression. Again, we do this with the pre-processing library from scikit-learn. So we can say from sklearn.preprocessing, and if you want, you should be able to tab autocomplete this. Then we're going to import polynomial features. Again, tab autocomplete that to make sure you're spelling it right, and then run it. And essentially, the way polynomial features works is it's in the same framework as just something like linear regression or any other model within scikit-learn. You create an instance of polynomial features, and then you can actually fit to your data set. So we'll explain what that means in just a second. So let's create an instance of polynomial features. For clarity, I'm going to say that polynomial converter is the name of my variable object, and then it's going to be an instance of polynomial features. Let's take a look at the main parameters we provide to polynomial features, and those are, if we expand on this, if we expand this, we have the degree. So degree is just to what order do you want to take the polynomial. As you can imagine, if you say degree is equal to 2, that means you'll also consider the squared terms of your features. So TV spend squared, radio spend squared, and newspaper spend squared. Later on, we'll have a discussion on how to choose the best degree to go to. In default, I would say just choose 2 and then slowly build up from there. But again, we'll show you how you can actually use multiple degrees, plot them out, and then decide which one's the best. The other things to consider are whether you want only the interaction terms. What's nice about polynomial features is it's also going to create interaction terms for you. So it's going to create TV times radio, TV times newspaper, and radio times newspaper. And sometimes people don't actually want to explore the higher degrees. They only want the additional interaction terms. So polynomial features can actually provide that for you if you say interaction only is equal to true. By default, it's false, so it'll actually also include those x squared terms as well. Then it offers the additional include bias term. If you include the bias term, that's just going to add in the array column of 1 values. Depending on what you're trying to do, that may be important for you, but in our case, we actually don't need that additional bias term since we're going to run linear regression on this afterwards. So we'll go ahead and say that degree is equal to 2, which is the same as the default, and then we'll say include bias is equal to false. So again, I'm not going to need that bias term, and I'm only going to say go to degree is equal to 2, and then we have the polynomial converter object. So for polynomial converter, what this is expecting is to be fit onto a data set. So we're going to come back up here and say, okay, we want to fit it to these particular features. And fitting, in this case, all it means is it's going to grab and analyze all the feature values. It's not actually going to transform anything until you ask for it. So we can say fit to our X data set. Keep in mind, we don't actually need to split this into a training set or test set yet, because this is not our machine learning model. It's just a feature converter. So we fit to X, and all that does is it basically says, here's the X data we want you to transform. However, if we actually want to transform it, we need to call polynomial underscore converter, and then say transform this X data set to some second degree polynomial. So you say transform X, run that, and you can see the transformed object. And you'll notice that if we check out the shape of this, it's 200 rows by 9 columns. Does that make sense to us? Well, if we think about the original X shape, it's 200 rows by 3 columns. It makes sense that we get back the exact same amount of rows. Let's explore if it makes sense that we get back these 9 columns from our 3 columns. Essentially what we have here is, if we look at XILOC0, I have these terms, 230.1, 37.8, and 69.2. Let's now save these results of the transform to polyfeatures is equal to polynomial converter transform X. And we'll discuss in a little bit the differences between fit and transform and a way you can call them both at the same time. But we're actually going to save the results of polynomial converter transform X to polyfeatures. Go ahead and run that cell. So now you should have polyfeatures. You should be able to check the shape of polyfeatures. And it should match 209. Okay, so let's take a look at the very first row of our original X and the very first row of polyfeatures. So we're going to say, go ahead and grab, using indexing, row 0. Okay, so we went from 230.1, 37.8, 69.2 to these 9 values. Does it make sense? Well, if you take a look at the first 3 values, those are actually just our original feature terms. This right here is 2.3 times 10 to the power of 2, which is the same as 230.1. So we have 230.1 here as the first term, 37.8 here as the second term, and 69.2 here as the third term. So the first 3 values right off the bat are your original x1, x2, x3. The next question is, where do the next 3 terms come from? Well, in that case, those are actually our interaction terms. So if we take a look at 230.1 times 37.8, I can say 230.1 times 37.8. The result there will be 8,697. And if you take a look at this value right here, that's 8,697. So these 3 terms are the interaction terms. And we can try that for another one. Let's go ahead and say, instead of times 37.8 times 69.2. So run that. We have 15,922, which is this number right here. And then finally, that was TV with radio, TV with newspaper, and then we have radio with newspaper, which should be 37.8 times 69.2. Run that, and we have 2,615, which is this value right here. So we do have all the interaction terms that we talked about. And then finally, we have the squared terms. So if I take, for instance, 230.1, square it. So we'll say 230.1, square it. We have 52,946. That number can be found right here. So the remaining 3 terms are the squared terms. So it makes sense now that we have 9 terms. The original 3, the 3 possible interaction terms, and then the 3 possible squared terms. And it's not in the exact order that we just presented. In fact, right here we can see that we have 5,246 coming immediately after the original 3, but we do now have all 9 terms necessary. Again, the 3 original, the 3 possible interactions, and then the 3 squared terms. So you just went from 3 features to 9 features, greatly expanding the feature set you can train your model on. Okay, so that's really the gist behind polynomial conversion. It's almost just like creating a new feature set to give yourself more signal for your upcoming linear regression. And essentially what we're going to do is train on polyfeatures and do our train test split on polyfeatures as if it was our original data set. Let's talk a little bit more about this .fit and .transform before we end this lecture. In general, many tools within scikit-learn ask you to first fit to the data in order to define the data range that you're going to be using. And then if you actually transform the data to some other data set, it will ask you to transform it. So there is this fit transform functionality happening here in 2 steps. Because it's so common to fit and transform on the exact same data set, there's also a fit underscore transform method. So what you can also do here is say polynomial underscore converter fit underscore transform, and it essentially does both steps at the same time. And in this case, fit is not really doing much. It's just analyzing what degree you want to go to and then taking in all the data. Transform is where the work is actually happening as far as creating a new data set. And so fit transform will run the exact same thing we just saw earlier in one single step. So you can either call fit on one line, then transform on another, or call fit transform to get the actual object returned in one line. Keep in mind that if you just call fit, it's not actually going to return anything. Nothing's returned until you actually call transform. And that's it for using polynomial features. Import it from pre-processing, decide on the degree and whether or not you want to include the bias term, or if you only want interaction terms. That's the converter object. Fit it to all your features, and then transform your feature set. And here we analyzed what that actually resulted in. Looks like we're ready for the next lecture, where we're going to perform the train test split and then fit our linear regression onto the polynomial data, which is essentially a polynomial regression. I'll see you there.